So in this video, we're gonna go over the solution for exam 3. So most of you did really well. I guess part of the reason is the open book. But anyway, because the error is high, so there won't be test correction. Right? So number one, so that's the definition for equilibrium. So the answer should be D, right? So we want to have the same reaction rate for the forward and the reverse reaction, right? Not the rate constant. Number two, we want to write down the reaction quotient QC for this reaction. So again, we don't want any solid or pure liquid phase in the expression. So water and this solid should not appear in the final expression, right? So the answer should be A. So the exponents are the corresponding coefficients in front of each substance. Number three, so you have a two reaction, right? So you want to calculate the equilibrium constant of reaction 2 based on the K value of reaction 1, right? So you have to look at the how we can change reaction 1 into reaction 2, so and modify the equilibrium constant K. Right, so if we look at this two equation, right, so first you have to flip it, right? So you have to minus the K1 minus the reaction 1 by multiply the reaction 1 by minus 1, which means you have to do 1 over K1, right? So that corresponds to multiply a minus 1, which is reverse the reaction, right? So then you have to look at the coefficients, right? So you have to multiply all the coefficients in the reaction 1 by 2 to match the coefficients in reaction 2. So you have to take the square, right? So that means you have to take the square of 1 over K1. So that is 1 over K1 square, right? So if you take the 1 over 276 square, right, you should end up with D. So next, we're gonna calculate this Kc value, right? So equilibrium constant. So at this certain temperature, right, this equilibrium concentration are given. So all you need to do is plug in these concentrations. So C is the product, and it has a coefficient of 2, so it's C squared. And A and B are the reactant, so they're on the denominator. A has a coefficient of 3 and the B has a coefficient of 2, so that becomes the exponent. So you just plug in those concentrations and the Kc will be D. Number 5, so you're mixing two reactants, and it tells you the equilibrium equilibrium concentration for both the reactants, and asks you the equilibrium concentration for the product. Right, so this is a simple version of the equilibrium calculation using the ICE table. Right, so because we need a concentration of each reactant product, so we have to convert the given values into concentration. Right, so you have a certain concentration of each reactant, right? They are the same, they're all 0.1 molar, but after you mix them, right? So after you mix them, their concentration changes due to this mixing, which is a dilution. Right, so you have to calculate their concentration after mixing. Right, so you have to calculate the number of moles, which is volume multiply concentration and divided by the total volume after mixing. Here I didn't convert milliliter to liter because the volume unit canceled out, so you don't have to do that. Right, so for each of the reactants, they have the same concentration, so 0.05 molar. And so you put them into the ICE table. So for the change of the concentration, the metal has a coefficient of 1, so it's minus X. The ligand has a coefficient of 2, so it's minus 2x. And the product is plus x due to the coefficient of 1. Right, so it tells you for L, the equilibrium concentration is 0.01 molar. That means the initial, right, plus the change, which is minus 2x, is equal to 0.01. So x is 0.02. Right, so for the product, the equilibrium concentration is 0.02. Right, so the answer is D. So number 6, we have this chemical equation. Right, so 2 gas generate 1 gas. Right, so it gave you the Kc value is 49, and gave you the initial amount of each gas in a certain volume reactor at the same temperature. So ask you what's the equilibrium concentration of this PCl3. Right, so it's one of the reactants. Right, so again, using the ICE table, right, so we can write down the expression for the Kc. Right, so using the ICE table, so first we want to know the initial concentration of the reactants, right? So we have the number of moles, we have the volume, right? So the 0.7 mole divided by 1 liter is 0.7 molar, and it is the same for both reactants, right? Because they have the same number of moles. So for the 2 reactants, we have 0.7 molar for each, and at the beginning there is no product. Right, so they're both 0.7, and there's 0 concentration of products. Right, so it's minus x, and this is plus x. So the equilibrium concentration of the reactant become 0.7 minus x, 0.7 minus x, and x. Right, so you plug in these 3 equilibrium concentration into the expression for Kc. Right, so you can solve for x, which is equal to 0.59. So 0.59 is value of x. Right, so that's how much product is produced in this case. But the question asks you the equilibrium concentration for PCl3, which is the reactant. Right, so it should be 0.7 minus 0.59. So the answer should be 0.11. A lot of you pick B, right? So, but that's not the equilibrium concentration, right? It should be 0.7 minus 0.59. So number 7, I made a mistake when I create this problem. I mean to ask you about the number of moles, right, for each reactant product, not the partial pressure. So I give everybody point for that. And so number 8, so you see this delta H is involved, right? So you know it has something to do with the temperature, right? So in this case, delta H is positive, so that means the heat is on the side of the reactant, right? So we can rewrite the reaction by putting heat on the left-hand side. So we want to produce largest amounts of oxygen, which is on the side of product, right? So we want this change of the reaction condition causing a net reaction or shifting to the right. Right, so we can either increase the amount of heat, which is increasing temperature. Right, so we want high temperature. Right, so A and C give you high temperature. And also in terms of high or low pressure, right? Remember, pressure and the volume has this inverse relationship, right? So we count the total number of coefficients for these gas molecules, right? They're all gases. So for the reactant, you have a coefficient of 2, but for your products, you have 2 plus 1, so it's 3. Right? So we want to increase the volume, right? Increasing the volume will shifting the reaction to the side with a higher total number of coefficients. Right? So we want to increase the volume. Increase volume meaning lower the pressure. Right? So we want high temperature and low pressure. So the answer is C. Number 9, asks for which is the strongest acid, right? So strongest acid meaning that the proton is the easiest to be donated, right? So or you want the hydrogen nonmetal bond to be very weak, right? So first, for B and F, right? So the hydrogen is attached to fluorine and iodine, right? So you know fluorine is very electron negative, right? So it doesn't want to lose that proton. So iodine is has a very low electron negativity, right? So that bond will be very weak, so the proton is very easy to get lost. So it is a stronger acid. So for the other three, remember the oxygen is actually connected to the hydrogen is actually connected to oxygen, right? So for this is COOH. You have this OH bond, and similar thing for the other two acids, right? So it's actually bonded to the oxygen, not the nonmetal, right? So oxygen also has a very high electron negativity, right? So HI is the strongest acid, and because it's an open book, right, you can also check their Ka values, or you can just Google it, right? So next, number 10, we want to compare the concentration of each species in a weak acid solution, right? So when you have a solution, right, so the amount of water will be the highest, right, because that's the solvent, right? So water auto-ionization is very weak, right? So most of the water molecules will remain as a whole molecule, right? So water will be the one with the highest concentration, right? Pure water is a 15.5 molar, which is very high, right? So next, because it's a weak acid, right? So for weak acid, it only partially, right, dissociate, right? So very little amount of the weak acid will dissociate and generating the proton under the conjugated base. So most of the acid remain as the acid molecule, right? So that's the second highest, and the amount of proton and the conjugated base is similar, right? So their amount is similar because this is acid. Right? Acid is acidic. Acidic means the proton concentration is greater than the hydroxide concentration, right? So the answer should be D. So number 11, we have a hydrobromic acid, which is a strong acid, right? So we add this acid into water and generating this solution with this pH, right? So we ask you the original molarity, right, which is the molar concentration for this HBr solution, right? So first, with the given pH in this final solution, right, we can calculate the molarity of the proton, right, which is 10 to the negative pH. So for this 482 milliliter solution, the proton concentration is 5.89 times 10 to the negative 5, right? So we know the concentration, we know the volume, so we can calculate the number of moles for the proton, which is concentration multiplied volume. So you have to convert the volume into liter, right? Because molar concentration is mole per liter, right? So you want to calculate the number of moles, you have to cancel out the unit of volume, which is liter. So you have to convert milliliter into liter. So this will be the number of moles for proton. And all of this proton come from the HBr you added, right? Because the water doesn't contain, it has a negligible amount of proton, right? So all this proton come from the HBr you added. So you know the volume, you know the number of moles, you can calculate the concentration, right? So the number of moles divided by the volume. Again, you want molarity, so you want that to be in liter, right? So that's the liter. So that's the molarity of the original HBr solution, right? So the answer should be A. Number 12, right? So again, you're comparing the strength of the acid and base, right, based on the direction of this acid-base solution, right? The rule is the stronger acid and base will generate a weaker acid and base, right? So in this question, it tells you that the products, right, the concentration of the products are greater than the concentration of the reactants, right? So meaning the reaction is preferred, right? So to the right hand side, right? So that means the left hand side are the stronger acid base and the right hand side the weaker acid base. So means this phosphoric acid, right, is a weaker acid than the oxalic acid, right? So this phosphoric acid on the right hand side is a weaker acid than the this oxalic acid, right? So the answer should be C. Number 13. So you can refer to chapter 18 I think 18.7, right? So talk about the acidity and the basicity for the salt, right? So if you want a salt to give you acidic solution, right, pH less than 7, you want a cation from a weak base, right? You want the cation of a weak base and the anion of a strong acid, right? So only B, ammonium bromide, give you this condition, right? So bromide, it comes from the hydrobromic acid, right? That's a strong acid. And ammonium is the cation of a weak base, right? Which is the ammonia, which is the weak base. So if you want a solution pH greater than 7, then you want a cation of a you want the anion of a weak base, right, and the cation of a strong acid. Right, so. Number 13. Oh, which is the number 13. Number 14. Right, so we have this compound which is a weak base, right? Why? Because the Kb value is given. The Kb value is very small, right? So it asks you the pH of a certain concentration of this weak base, right? So similar to Ka, right? We can express Kb using this equation. Notice water here is liquid, so it's not involved in this expression. So using Kb, right? So we can list the ICE table, right? So calculate X, right? Again, this denominator should be 0.025 minus X, but because this Kb is very small, so we can ignore that. And then we can calculate X. X is the hydroxide concentration, right? So you can convert hydroxide concentration into POH, and then using 14 minus POH, that will be the pH. So the answer is C. Next, number 15. Right, so which one of the following 0.1 molar solutions will produce a buffer solution when they're mixed? Right, so for a buffer, you want them to have a common ion effect. Right, so and this common ion should be from a weak acid or base. Right, so E, the last one. Right, so this acidic group, acetate. Right, so you have the weak acid and the corresponding salt, right? So that will give you this buffer solution. Number 16, which one of the following should be used to prepare buffer with a pH of 4.5, right? So when we select the buffer, remember there are a few rules that we need to follow, right? So the first rule is that we want this pKa, right? So pKa close to the pH, desired pH, right? So we want a pH 4.5, so we see which acid has a pKa value close to that, right? So the acidic acid has a pKa of 4.74, which is close to the desired pH. So we pick C. Number 17, right? When a strong acid is titrated with a weak base, the pH at the equilibrium point, so that will be that less than 7, right? So when you titrate, right? So when you titrate strong acid, strong base, the equivalent point pH is equal to 7. Right, so when you titrate a let me write that down, right? So if you titrate a weak acid with a strong base, right? So the equivalent pH is greater than 7. Right, so if you titrate a weak base with a strong acid, the equivalent point, right, pH will be less than 7. Right, so in this case, you titrate a weak base with a strong acid. Oh, you titrate strong acid weak base, so that's similar to this condition. Right? So the equivalence point pH is less than 7. Number 18. Right, so you have this weak acid, right, so free chlorine. So you titrate that with strong base. Right, so the concentration of the weak acid and the strong base is the same. Right, so remember, in this case, there's a very special point. Right, so you can use this. No, actually, let me draw it. You have this buffered region, and then this equivalent point again is greater than 7. Right, so if this is a 7, this equivalence point is pH is greater than 7. But remember, in the middle, it's halfway to the equivalence point, the pH is actually equal to pKa of the weak acid. Right, so it asks you the Ka value. Right, so if you want to know the Ka value, you want to know the pH at the halfway to the equivalent point. Right, so because the acid and the base had the same concentration, so you're gonna use the same amount, which is 20 milliliter of the base, to reach the equivalent point. Right, so 20 is the equivalent point, so half of that is 10 milliliter. Right, that's halfway to equivalent points. The corresponding pH is equal to pKa. Right, so the Ka for this acid is equal to 7.46. Right, so the pKa will be 10 to the negative of Ka value, which will be B. Number 19 is related to the solubility. Right, so solubility of a metal salt, right, of a salt, is basically the amount of this metal cation generated when this salt dissolves. Right, so in this case, we have lead chloride, and then we want to know the solubility constant. Right, so we can write out this equation. So the salt gives you the metal and the 2 chloride. Right, so first we can convert this solubility, which is in gram per 100 milliliter, into molarity. Right, so 4.5 is the mass. We want the molarity. We want number of moles. So you divide the mass by the molar mass of this lead chloride. Right, so that gives you 0.0162 mole. Right, so notice here I multiplied this solubility by 10 on both the numerator and denominator. Right? So I convert the 100 milliliter to 1 liter, and so 0.45 become 4.5. Right? So after I did this, the unit will be in mole per liter. Right? So this will be the amount of lead generated. So for the chloride generated, it will be twice of that, right? Because the coefficient 2, so I multiply that by 2. So the KSP will be lead concentration times the square of the chloride concentration. So remember the square. So the answer should be B. Number 20 is related to the change of solubility per dust concentration, right? When we affect this equilibrium. So here we have manganese sulfide generating this hydroxide. Right, so the question asks, how is the solubility affected by the addition of aqueous potassium hydroxide? right? So remember for this type of calculation, right? So there's a rule that because the same temperature, right? So KSP doesn't change. So when the concentration of one of the product increase, the other will decrease. Right? So if you increase the hydroxide concentration by adding potassium hydroxide, which is a totally soluble salt, right? So that means the manganese concentration will decrease, and manganese concentration is referred to the solubility of this compound, right? So the solubility will decrease. Now let's jump to the short answer, right? So this first one is very similar to the one in the practice exam, right? So most of you did really good, but many of you still have trouble doing this type of calculation, right? When this type of equations are involved, like this, right? So for this one, we have 2A generating B and C. The initial concentration of A and B are given, right? So we convert the number of moles and the volume into molar concentration. So you have 0.8 molar of A and 0.2 molar of B, right? So have no C at the beginning, right? Some of you forgot to convert the numbers, right? So, and then the change of concentration, so A, because the coefficient 2, so it's minus 2x. But here I use a negative sign because there's no C at the beginning, right? So I know some C will be rated, right? So I know C concentration is going to increase, B will increase, so A must be decreased, right? So I use minus 2x. And for B and C is plus x, right? So these are the equilibrium concentrations, right? So I have Kc, so you have equilibrium concentration of B times equilibrium concentration of C divided by the equilibrium concentration of A square. Remember this square, a lot of you forget about this square, right? So to solve this equation, right, so you can open this up, right? So on top you have 0.2x, right, plus x squared. At the bottom you have right, so 0.8 squared is 0.64, right, minus 2 times minus 2 times 0.8, which is 3.2 x, and plus 2x squared, which is 4x squared, right? 2x times 2x, 4x squared, and that equal to 0.5. And some of you forgot to multiply 0.5, right? So you can move the denominator on the right hand side, so all the number you multiply that by 0.5, so that equation become 0.2x, right? So the numerator is the same. So on the right hand side, you be 0.64 times 0.5 is 0.32. Right? So then minus 1.6x plus 2x squared, right? 2x squared. So you can move this to the right hand side. So on this side you have 0. So here you still have 0.32. And then it's minus 1.6x minus another 0.2x, that's minus 1.8x. And then 2x squared minus x squared is x squared, right? So you're solving this equation, right? So that will be right on this side, right? 2a, a is here, a is equal to 1 for the x squared, right? So that's 2. And you have minus b, right? So minus 1.8 is positive 1.8, and plus minus square root of 1.8 squared minus 4 times 1 times 0.32, right? So just solve for this, you get a 0.2 and a 0.9. So 0.9 is not realistic here, right? So because you cannot have a negative concentration at the end. So only 0.2 is reasonable, right? So x is equal to 0.2. But the question asks you the equilibrium concentration of A, right? So for A is 0.8 minus 2x, so it should be 0.4. So in B, so in part A, you reach this equilibrium, right? So in B, you add another 8 moles of A into this equilibrium system. So you disturb it, right? So you disturb it. So the amount of A added, right, will be equal to the 8 divided by volume, which is 10, right? So you add another 0.8 molar of A. So at the initial equilibrium, you have 0.4, right, left. You add another 0.8, so that becomes 1.2, right? So that's 1.2 here. So for the concentration B at the initial equilibrium, you have this initial concentration, right? So this amount generated, so that is 0.4, and for C is X, which is a 0.2, right? So this is the initial concentration, right? So after this equilibrium is disturbed, right? So you use the same rule for the change of concentration. So this will be the equilibrium concentration for A, B, and C. And you can plug in these values into the expression of C, right? So as I told you, you don't have to calculate it. Right, so you just plug in these numbers and then solve for X. So the new equilibrium concentration will be 1.2 minus this 2X. Number 22 is very simple, right? So it's a buffer solution, right? So yeah, we have the mass of each component. So we have to convert the mass into molar concentration, right? So the volume is given, it's 1 liter. Right, so first convert the gram into number of moles, right, using the molar mass, and then divided by the volume, you get the molar concentration. Right, so next you can use the equation that pH equal to pKa of the weak acid, right? So it's given, right? So plus the log of the base, right? So base is the fluoride, right? So conjugated base, that's the concentration here, and divided by the concentration of the acid, which is HF, right? So that will give you about 2.54. Right, so this is a simple way, and most of you did this way. Right, so another way to do it, right? So is listing out this ICE table, right? So for this acid to dissociate, generate proton and conjugated base, right? So you know the initial concentration of the acid and the base is a change of concentration, right? So it's the equilibrium concentration. You can, based on the K value given, right, calculate for X, and X will be the amount of proton generated, right? So if you do that, you're gonna get the same result, right? So by converting the proton concentration into a pH, right? So you get the same result. Right, so both way works, and the first way is much easier. Number 23, so is a titration between the weak acid and the strong base. Right, so it's also similar to the practice exam. Right, so for A, it asks you the pH when 10 meter of this strong base has been added. Right, so some of you say it's equal to 7, but remember, when the equivalent point pH is equal to 7, that's for strong acid, strong base. Right, so this is a weak acid. We know for weak acid, strong base, the equivalent pH is actually greater than 7, right? So if you get something less than 7, that means you definitely did something wrong, right? So the answer should be greater than 7, right? So in this case, right, you have the volume of the weak acid, the molarity, so you know the total number of moles, right? So for this 10 meter of sodium hydroxide added, right, I'd like you to figure out the number of moles of the weak acid is actually equal to the number of moles of the hydroxide added. Right, so all the weak acid has been consumed by the base added, by this 10 meter of sodium hydroxide. Right, so you have no HA left in this case. So all the HA has been converted to its conjugated base form. Right, so but the concentration, right, will be smaller because the volume increased, so it's been diluted. So initial concentration of HA is 0.25, but you add another 10 milliliter of base solution, right? So the final volume becomes 30 milliliter, right? So you have to convert that concentration, right? So if you say, move down a little bit, so clear that. Right, so this is the initial concentration of the weak acid, which is 0.25, right? But it's been diluted, right, due to this volume change. So this is actually the equilibrium concentration, with the concentration of the weak base at the equivalent point, right? So A minus the weak base, the conjugated base of the weak acid. So this is what you have, right? So, and you generate this little bit amount of the acid and the hydroxide, right? So based on the Ka value, we can calculate Kb, right? In this case, you generate hydroxide, so we should use the Kb value. So Kb is equal to Kw divided by Ka. So you can calculate this Kb value, right? So the result of this term is the Kb value, and the Kb will be equal to the x squared, right, divided by 0.167 minus x, and we assume x is very small, so we can just use 0.167. So calculate the x equal to this, which is hydroxide concentration. Convert that into POH, right? And then using 14 minus POH, right? So that will be the pH of the solution, right? So yeah, POH is 5.07, so pH is 14 minus 5.7, 0.07, so it's equal to 8.93. Right? So about 1/3 of you got this one, right? Right, so for part B, it asks you what's the pH of the system when 25 milliliter of the sodium hydroxide has been added. Right, so we know that 10 milliliter reached the equilibrium point, right? So for 25 milliliter, that's an extra of a 15 milliliter of the strong base added, right? So although we know that, right, the A minus, which is the weak base, also exists, but compared to the strength of this strong base, we can ignore that weak base, right? So the pH mainly controlled by this 15 milliliter of extra sodium hydroxide added into the system, right? So we can say that the amount of sodium hydroxide added in extra, right? So will be 15, which is 25 minus 10. Right, so this 15 milliliter of extra sodium hydroxide will determine the pH of the system, right? So this volume, right, times the concentration of this sodium hydroxide divided by the total volume, which is the original volume of the acid. You add 25 milliliter, so the total volume is 45. Again, I didn't convert milliliter to liter because I have milliliter on both numerator and denominator, so they cancel out. So the concentration of the hydroxide in the system after 25 milliliter of this sodium hydroxide added is 0.167. Right, so some I'm really curious, like some of you got this part right, so got the number of moles in extra and also got the final volume, but you got this number wrong, right? All of you got 0.6. I don't know how you get that, right? So it should be a 0.167 mole per liter, right? So that's the hydroxide concentration. You convert that into POH, which is 0.78. So pH is 14 minus 0.78. That is 13.22. So if you look at the chapter 19.2, so for the titration between weak acid and the strong base, right? So the example is given, right? So you can use the same approach for this type of problem. Right, so some of you, for part one, some of you use the equation for the buffer. But here you at equivalence point, you already passed that buffer region, right? So no acid left, so HA concentration is 0. So the denominator is 0, you cannot have something with a 0 denominator, right? So you can no longer use that equation. The last one, so Dr. World Peace, right? So right now we hope for world peace, right? We hope for this virus to be eliminated, right? So I use Dr. World Peace here. So he trying to form this precipitate calcium hydroxide, right? So he add this potassium hydroxide, which is a totally soluble salt, into a calcium nitrate, which is also totally soluble. Right, so you have the calcium, you have the hydroxide. So you want to know whether this precipitate is gonna form or not, right? So in this case, we want to compare the QSP with the KSP. Right, so if the QSP is greater than KSP, it will form, right? So the precipitate will form. But if the QSP is less than KSP, it won't form. So here we want to first, right? So this solubility equation, right? So it give you 1 calcium, 2 hydroxide. We want the molar concentration of each of the product, right? The molarity, not the number of moles, right? So to calculate molarity, calcium is already given, right? So it's 0.001 molar. So it's already given. You don't have to do anything with it, right? So it's 0.001 molar. And if you add this potassium hydroxide, in this case, you can just assume this is the solid, right? So it doesn't change the volume of the solution, right? So you have the number of moles of the hydroxide, you have the volume. So the concentration of hydroxide will be moles divided by the volume. So that's 0.015 molar. That is the hydroxide concentration. Right, so you have to square this concentration, right? Because the coefficient 2, a lot of you got to do the square, right? So it's for the QSP is calcium concentration times the hydroxide concentration square. So you got this QSP, which is smaller than KSP. So we say no precipitate will form. Right, so for this exam, right, a lot of you did really well, and so I think this format works, and so I will continue to do this format. And I think more than half of you actually pick this current format, right? Because you can pause the video anytime you want and study the lecture anytime you want, right? Based on your schedule. Some of you prefer doing the Zoom live session because you think you want to keep this schedule, right? That force you to follow. But I don't understand, like you can just like watch the video on the class time, right? So the video is posted before the class time. So how about just watch the video during the class time, right? So if you're in the 9:15 to 10:15 lecture, just make yourself watching that video during that time. Right? So I think because based on the result of the exam, I think this format works pretty well, right? So I'm gonna continue doing this format. I will upload video lectures right before the class time, right? So you can watch it. And also, please, right? So if you have any question regarding any content of the video lecture, just we can do like Zoom or FaceTime or email test, right? So a lot of you did that before the exam, asking me the question regarding homework. And for those students, they did really well on the exam, right? So I highly suggest you, right? So don't be shy, just like contact me, right? During daytime, 9 a.m. to 9 p.m. anytime you want, right? If you text me, I will get back to you as soon as possible because I check my message more often than email. And so we can either do FaceTime or Zoom, to help you. So I've still assigned homework for the last 2 chapters, but I won't collect the homework, right? But you're gonna find doing the homework is gonna be very, very helpful for you to study the final exam, right? For the content of the last 2 chapters in the final exam, right? So for those of you who did the homework 3 seriously, they also got a very good grade on the exam. All right, so that's it.